NVIDIA is often described as the company powering the AI revolution. It has turned silicon chips into something that looks a lot like intelligence, and it makes things that seemed impossible a decade ago feel normal today. How did that happen? Hey everyone, welcome back to the channel. My name is Gaurav, and in this video, we are going to do a deep dive into NVIDIA. This is part 1 of a 2-part deep dive. In this part, we will cover how NVIDIA started, how GPUs and CUDA evolved, how it entered AI, how it pivoted into data centers, and how the business is structured across its 4 main segments. In part 2, we will go deeper into the software stack, what NVIDIA actually sells as a full stack platform, its financials, competitors, culture, and why it is not just a chip company. If you're interested in stocks, technology, or are just curious about the companies shaping our future, this video is meant to be a clear, step-by-step breakdown you can use to form your own view on NVIDIA as a business and as an investment. NVIDIA is quietly becoming the operating system of artificial intelligence, the toll road inside data centers, and the picks and shovels business behind almost every big AI model you have heard of. If you removed NVIDIA from the world tomorrow, OpenAI would struggle. So would Meta, Google, Amazon, Tesla, and almost every serious AI startup on the planet. In this video, we are going to unpack exactly why that is. We will go from the origin story and GPUs to CUDA and software and to AI and data centers. Let us start with how NVIDIA began and how it became what it is today. Because to understand the company now, you need to see where it came from. NVIDIA was founded in 1993 by Jensen Huang, Chris Malachowski, and Curtis Priem. Their goal was to improve computer graphics using specialized hardware. Early on, they focused on building graphics processing units or GPUs, a term they themselves coined. A GPU is a chip designed to do a huge number of simple calculations at the same time. This is called parallel computing. A CPU, which is the main processor in a computer, tends to process things in a more sequential way, while a GPU can process billions or even trillions of tiny operations in parallel. Their big breakthrough came in 1999 when NVIDIA released the GeForce 256, which they called the world's first GPU. It changed PC gaming by moving most of the graphics work away from the CPU and onto this new chip. That shift gave gamers smoother performance, higher frame rates, and better looking games. From the beginning, speed and constant improvement were part of NVIDIA's culture. After the first GPU, they adopted a fast release cycle and pushed out new or upgraded chips roughly every 6 months. That helped them stay ahead of competitors, and it trained the organization to move fast. A big reason they can focus so heavily on innovation, even today, is because NVIDIA is a fabless chip designer. That means they design the chips and the architecture, but companies like Taiwan Semiconductors manufacture the wafers in their advanced fabrication plants. NVIDIA does not have to build and run its own chip factories. That structure lets them put more of their capital and energy into design, software, and systems instead of into physical manufacturing facilities. Once NVIDIA had this strong hardware base in gaming, the next step was to turn those GPUs into something more flexible than just graphics engines. This is where software enters the story. Originally, GPUs were mostly fixed function devices. They took graphics commands from the CPU and turned those into pixels on the screen. That was perfect for games and user interfaces, but not very flexible for other types of computing. Inside NVIDIA, some engineers started asking a different question. What if we could program the GPU directly as if it were a small supercomputer? Out of that idea came CUDA. CUDA is a parallel computing platform and programming model that NVIDIA started building in the mid-2000s and released publicly around 2006. It gave developers a way to treat the GPU as a general-purpose processor for many kinds of workloads. Over time, CUDA evolved into a large software platform. It allowed developers to write code in familiar languages like C and C++ and run that code on the GPU. This turned the GPU into a flexible tool. They could send large blocks of computation to thousands of GPU cores and get results much faster because of the parallel computing model. Today, CUDA and the related CUDA-X libraries support millions of developers and have hundreds of millions of downloads. NVIDIA provides this software for free, but it only runs on NVIDIA hardware. That means every researcher and engineer who learns CUDA and builds their tools on top of it becomes another person effectively tied into the NVIDIA ecosystem. The software layer is NVIDIA's first major moat. Now, it is not just about building fast chips, but about creating the full environment of tools, libraries, and workflows that make those chips easy and powerful to use. And that is exactly what set NVIDIA up to become central to modern artificial intelligence. So far, we've talked about how NVIDIA turned GPUs from fixed function graphics chips into programmable supercomputers using CUDA. Once that happened, something important occurred outside of NVIDIA, in the world of artificial intelligence. For decades, AI researchers had been experimenting with a type of model called a neural network. The idea of a neural network is to loosely mimic how neurons work in the brain. You have layers of nodes or neurons connected to each other. Each connection has a weight, and by adjusting these weights using data, the network can learn patterns such as recognizing objects in an image or understanding speech. The problem for a very long time was not the idea, it was the compute. To train a neural network, especially a deep one with many layers, you need to perform a huge number of mathematical operations. At a high level, most of this boils down to matrix multiplications and small calculations repeated over and over again. In the 1980s and 90s, computers were simply not fast enough to train big, deep networks on large datasets, so a lot of early AI enthusiasm cooled off. This is where GPUs and CUDA quietly became a turning point. GPUs were already designed to do many simple operations in parallel. With CUDA, researchers now had a way to program those GPUs directly for non-graphics workloads. Around the same time, there was another important development in the AI world: the rise of large datasets. One of the most important datasets was ImageNet. ImageNet is a large collection of labeled images organized into thousands of categories such as dog, car, or tree, and many others. It became the basis for an annual competition where teams would build models to classify images as accurately as possible. This competition turned into kind of an Olympics for computer vision research. Before 2012, the best performing models in the ImageNet competition used more traditional machine learning methods and hand-engineered features. Accuracy was improving, but only gradually. In 2012, that changed. A team from the University of Toronto built a deep neural network called AlexNet and trained it on NVIDIA gaming GPUs. Because GPUs could perform massive number of operations in parallel, they were able to train a much larger and more complex model than what had been practical on CPUs. The result was a shock to the field. AlexNet's performance on the ImageNet competition was significantly better than the previous best models. The error rate had sharply dropped in 1 year, and it became obvious that deep learning combined with large datasets and GPU compute was a new path forward. That single result did two important things. First, it proved that deep neural networks, which had been around in theory for decades, could suddenly leap ahead of older methods when they were combined with enough data and enough compute. Second, it showed very publicly that NVIDIA's off-the-shelf gaming GPUs programmed with CUDA could act as the engine behind this new wave of AI. From that point onwards, AI research started to scale up quickly. As more teams adopted deep learning for image recognition, speech translation, and later for language models, the amount of compute used in the largest training runs began to grow at an extraordinary pace. OpenAI and others later showed that compute used in cutting-edge training runs was doubling roughly every few months. In simpler terms, every new state-of-the-art model required much more computational horsepower than the one before it. Now, because GPUs could be linked together and because CUDA provided a flexible programming environment, NVIDIA became the default hardware platform for this acceleration. Instead of building custom chips from scratch, many researchers and companies chose to stack NVIDIA GPUs into clusters and use deep learning frameworks built on top of CUDA. By the middle of 2010s, even though many consumers still thought of NVIDIA as the graphics card company, inside AI labs and large technology companies, NVIDIA had become the engine room of modern deep learning. Inside NVIDIA, Jensen and his team could see exactly what was happening. AI was no longer just an academic project. It was turning into a major wave of computing. That realization is what sets up the next part of the story, where NVIDIA pivots from being a gaming and graphics company to becoming an AI data center infrastructure company. Once NVIDIA understood how central its GPUs and CUDA had become to deep learning, the next question was obvious. If AI was going to keep growing, where would all of this compute actually run? This was not just about a few GPUs under a researcher's desk anymore. It was about large clusters of GPUs inside massive facilities called data centers. A data center is essentially a warehouse full of servers and networking equipment that runs the applications and services we all use every day. NVIDIA realized that if it wanted to be at the center of this new wave, it could not only be a graphics company. It needed to become a core part of data center infrastructure for AI and high-performance computing. So the company pivoted. NVIDIA started describing itself less as a gaming company and more as an AI data center infrastructure company. A few strategic moves defined this pivot. They shifted the CUDA and GPU roadmap towards AI and high-performance computing workloads instead of only gaming workloads. They built complete systems like the DGX line. A DGX system is essentially an AI supercomputer in a box, with multiple GPUs, high-end CPUs, fast memory, and networking. They acquired Mellanox, a company that specialized in high-speed networking for data centers. This let NVIDIA control the fast data pipes inside supercomputers, not just the chips. They expanded into software platforms such as NVIDIA AI Enterprise and Omniverse so that they could sit higher in the software stack, not just at the chip level. You can see the impact of this pivot in the numbers. In 2020, gaming was still the largest business, making about half of NVIDIA's revenue. Data center was only about a quarter. By 2025, data center revenue had jumped to around $115 billion and made up close to 90% of NVIDIA's business. That is a dramatic shift in the company's core in a very short period of time. Now that we've seen the pivot, it is helpful to break down the four major segments NVIDIA reports so we can understand where all of this revenue is actually coming from. Officially, NVIDIA reports revenue from four markets: data center, gaming, professional visualization, and automotive. Let us walk through each of these and connect them back to the bigger picture. Gaming is where NVIDIA built both its foundation and its brand. The GeForce line powers a huge share of gaming PCs around the world, and for many years, gaming made up almost half of NVIDIA's total revenue. Even today, NVIDIA has a dominant position in discrete PC GPUs with the RTX series as its flagship. What makes NVIDIA's gaming business important is that it has always been a place where the company pushes the limits of graphics technology and increasingly artificial intelligence. For example, one major shift they led was ray tracing. In older games, lighting was approximated using shortcuts and tricks. Ray tracing is a technology that tries to simulate real light, how it bounces, reflects, and behaves in the real world. That is extremely challenging for a GPU, so NVIDIA added dedicated ray tracing cores to handle it. Another major innovation is DLSS, or Deep Learning Supersampling. Instead of relying only on raw power to render games at higher resolutions, DLSS uses AI to upscale images. The GPU renders the game at a lower resolution and a trained neural network reconstructs a sharper image. That means better graphics and smoother frame rates without needing huge increases in hardware power. Both ray tracing and DLSS show how NVIDIA blends AI and traditional graphics to keep gamers loyal and to stay ahead of competitors. And gaming is no longer just tied to the customer's PC. With GeForce Now, NVIDIA runs the game in its data centers and streams the gameplay to any device. This is another example of how gaming connects directly to the data center infrastructure NVIDIA is building for AI. Data center is now the heart of NVIDIA's growth story. In this segment, the company sells hardware and software that power AI workloads and high-performance computing for customers like hyperscale cloud providers, research institutions, and large enterprises. Hyperscale cloud providers are companies such as Amazon, Microsoft, and Google that operate very large data centers and rent out compute to others. This is the largest segment today, and NVIDIA GPUs are widely viewed as the gold standard for AI. A few product families are central here. There are GPU chips like the A100, H100, H200, and the newer Blackwell and Rubin lines. These are designed specifically for AI and other heavy compute workloads. There are DGX systems, which are fully integrated AI servers with multiple GPUs, high-end CPUs, large amounts of fast memory, NV switch fabrics, and all the necessary software installed. You can think of DGX systems as self-contained AI factories. There is networking hardware. Through Mellanox and its own internal network, NVIDIA sells Ethernet cards and high-speed switches. It also offers NVLink and NVSwitch, which provides extremely fast connections between GPUs, much faster than the standard PCI Express. As models and datasets grew larger, connectivity and bandwidth became major bottlenecks. NVIDIA saw this coming and built NVLink and NVSwitch to push data between GPUs at very high speeds. At a high level, the data center segment is where NVIDIA no longer just sells individual chips, it sells entire racks and clusters that form the backbone of AI data centers. Professional visualization is NVIDIA's business for designers, engineers, and professional creators. In this market, NVIDIA sells workstation GPUs for tasks such as computer-aided design, film and animation rendering, medical imaging, and high-end content creation. The products include professional versions of their GPUs like Quadro and RTX for workstations, and software such as Omniverse. Omniverse is a platform for building shared virtual environments and digital twins. A digital twin is a virtual representation of a real-world object or system such as a factory, robot, or a supply chain. The segment is smaller in terms of revenue than data center or gaming, but it's strategically important. For example, Omniverse lets companies simulate factories, warehouses, robots, and even cities in three-dimensional virtual space before anything is changed in real life. That fits into NVIDIA's vision of an industrial metaverse where digital and physical systems are closely connected. The fourth segment is automotive and robotics. Here, NVIDIA sells platforms such as Drive and Jetson. These are compact systems that bundle GPUs, CPUs, and softwares for self-driving features, advanced driver assistance, and in-car AI. They process data from cameras, radar, and other sensors in real time. NVIDIA also offers AGX systems, which are smaller supercomputers. These are used in cars and autonomous machines. At the moment, automotive is still small compared to data center, but as cars become more like connected computers on wheels, and as robotics becomes more common in warehouses and factories, this segment could become a more important long-term growth option. Now, so far, we've gone from NVIDIA's origin story to GPUs, CUDA, AI, the pivot into data centers, and how the four main segments fit together. In part 2, we are going to move one level deeper. I will break down NVIDIA's software stack and this idea of full stack AI platform, what the company actually sells from chips to systems to cloud, how the money flows through the business, why the financials look the way they do, what Jensen has built culturally inside the company, and finally, why I do not think NVIDIA is just a chip company. Thanks for watching part 1, and I will see you in part 2.